Hi. The material in Chapter 17, Sections 1 through 3 is an extension of the material in Chapter 16, which you remember was about identification numbers. An identification number like an ISBN or a UPC code number is designed to do two things. One is provide a unique identification, and two is to give some chance to be able to correct errors. So that thought continues into Chapter 17, and I'll say more about that in a moment. But first, let's cover some background mathematics that I would like to use. This page is not in the textbook and you are responsible for it. So here's modular arithmetic in a nutshell. It's designed to answer questions like, if it's currently a Thursday, what day of the week will it be in 10 days, in 100 days, in 1,000 days? How do you go about doing questions like this efficiently without just having to count on your fingers, say? Let's think about the idea of a clock, which we draw arranged in a circle, an analog clock at least, and after it is 12 o'clock, it doesn't become 13 o'clock and 14 o'clock. We go back and start over, so to speak. We don't usually draw days of the week that way, but in terms of how it works, it's the same. Let's draw a circle and put the days of the week on it. So there's Sunday and Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. And the reason it's appropriate, again, to put these in a circle is after Saturday it becomes Sunday again, and then back around to Monday, Tuesday, and so on. Further, let me go ahead and number these. I'm going to start with 0 here at Sunday, and then 1, 2, 3, 4, 5, 6. Now, by this numbering scheme, it's currently a Thursday. That is day 4. And so let's answer question 1. If it's currently a Thursday, that is day 4, and we wait 10 more days, what day will it week? Well, 4 plus 10 is 14. The answer is it's day 14. But I look at my week clock, days of the week clock, and I don't see 14. The question is now, where is it? So if you think about it, let's take a simpler question for a moment. Where's day 7? Well, I would count up 1 through 6 and then back to 0, but that is day 7 as well. 7 and 0 are the same thing in terms of days of the week, and 8 and 1 are the same thing, and 9 and 2 are the same thing, and so on. So if I'm counting to 14, I go around once and get 7, and then 8, 9, 10, 11, 12, 13, 14, and I'm back at 0 again. Here's another way of identifying that, a more organized way. Here's 14 days, and I'm only interested in where I am relative to a count of 7. So let's take 14 divided by 7. We get 2. And if I think about the long division, which you hoped you would never have to do again, the remainder is 0. So what this means is 14 days is 2 trips or 2 weeks around the circle, and then no more after Sunday. So the answer is Sunday, day 0. And what about this computation told me it was day 0? It's the remainder, not the quotient, but the remainder. That's the important part here. So how about if I have 100 days pass starting from Thursday? Well, 4 plus 100 is 104. Question, where is 104 on the days of the week circle? I take 104 and divide by 7. Goes in once, remainder 34. Now goes in 4, 28, leaves 6 left over. So again, the remainder is what's important. Day 6 is, from the chart, a Saturday. All right, and third, and now the numbers are getting bigger, but we have a system, we know what to do. 4 plus 1,000 is 1,004. And if you take 1,004 and divide it by 7. I'll use this notation this time. 1004 divided by 7 works out to be 143 remainder 3. Alright, you can do the long division if you want and show that you have a remainder of 3, which by our days of the week is a Wednesday. So for computations like this, the remainder when we do a division is what's important to keep track of. Mathematicians use the term modulus for remainder. So in particular, they say things like 7 mod 5, and what is that? Well, it's a number. It means what happens when you take 7 divided by 5 and look at the remainder like we were just doing. 7 mod 5 is 2. How about 17 mod 12? So you take 12 into 17, it goes once, and there are 5 units left over. 17 mod 12 equals 5. How about 6 mod 12? Careful here, it's not 12 divided by 6, it's 6 divided by 12. So if you think about this, this is crazy. 12 doesn't go into 6, it goes in 0 times, in other words, and the remainder is 6. 6 mod 12 is 6. Or how about problems involving arithmetic? What's 13 plus 19 mod 5? So this means take 13 and 19, add it together, then divide by 5, and what's the remainder out of that problem? Let's try a sneak attack. It actually turns out to be easier to do the mod first, to find the remainder first before you add. The numbers are smaller that way. So how about 13 mod 5? Well, that's 3. 5 goes into 13 twice with 3 left over. And 19 mod 5? 5 goes into 19 3 times with 4 left over. And so now it's easier to add 3 and 4, and you get 7 mod 5. And what is that? Well, 5 goes into 7 once with 2 left over. So the numerical answer is 2. Let's look at a very important special case when we're doing mod 2 computations. What's 18 mod 2? So I take 18 divided by 2 and ask what's the remainder. Well, that goes in evenly, so the remainder is 0. On the other hand, when I take 15 mod 2, that goes in 7 times with a remainder of 1. And if you think about it, these are the only two things that can happen. If you're dividing by 2, you can either have a remainder of 0 or you can have a remainder of 1. And in particular, we can say exactly when that happens. A number mod 2 equals 0 if, so why did this work out to be 0? Because the 18 is an even number. And then in a similar way, why did this work out to be remainder 1? Because 15 is an odd number. So in general, a mod 2 equals 1 if a is odd. So in the special case mod 2, we don't even have to do the division. We just look at whether the number is even or odd and write down either a 0 or a 1. That's modular arithmetic. So tuck that in the back of your mind, and let's go on and talk about why we want to talk about coding. So we talked about identification numbers in chapter 16, ISBNs and UPCs in particular, and those were base 10 numbers. So an ISBN can be 3, 7, 4, 6, and so on. We have a base 10 number system that we use as humans, but as you probably know, computers don't use base 10 internally, they use base 2. So zeros and ones are the only possible characters in a computer transmission of information. In particular, if you're typing something, as soon as you push the letter A on the keyboard, the computer internally converts it to a sequence of zeros and ones that's unique to the letter A. And then you type D, and then the computer converts that to another sequence of zeros and ones. And when you send that in an email to a friend or something over the internet, goes this something like this, a string of zeros and ones. It's received and decoded at the other end by the computer. We call those binary codes, binary or base 2 codes, as opposed to the base 10 identification numbers we were talking about before. And we'll call a binary digit a bit. So in a string of zeros and ones, each individual 0 or 1 is called a bit of information. Now, if you have 4 bits to use, it turns out that you can code information as follows. This is more or less arbitrarily chosen, but it does make sense. There is a pattern going on here. I could say that a space, for example, I'm going to encode as 0000, and the letter lowercase a 0001, b 0010, and so on. If you've ever counted in base 2, what we're doing is counting up from 0 to 15 actually in base 2. Alright, so here is the code, binary code that I decide to use, and now if we at our keyboard type a good job, a space G-O-O-D space J-O-B, the information lookup is as follows, just pulling for each letter its associated code word, and then what I do is just send this string of bits all packed together like this across the internet to another computer. So a good job looks like this when I use this binary code. Given that, then what happens if you, the receiving computer, see this piece of information coming in? What does it say? Well, okay, I happen to know that each code word is 4 bits long, so the right thing to do is to break this into blocks of 4 bits. And then just one by one look up the string of 4 bits in the alphabet in the code book. So 1100 happens to be an L, and then an E, G, space, O, F, space, L, A, M, B. So why you would want to type leg of lamb, I have no idea. But if you did and used this particular coding scheme, this is what the message would look like. Okay, let's talk about what a code is supposed to do. One is a code should be able to ensure accuracy. Just like with the ISBN and UPC, we want the capability to be able to detect errors, or perhaps even to correct errors. The computer at the other end, at the receiving end, says, uh-oh, I've received something that's not a valid code word. I know there's a problem. Maybe I can even correct it at my end. If I can't correct it, at least I can send a message back to the computer that's talking to me and say, hey, I've received something that seems wrong. Could you send that word to me again? And this does happen on the internet. There are noise signals on the internet, and sometimes errors are made, and if you have a good code, the receiving computer asks the transmitting computer to do a retransmission. Another thing that a code should do is be able to be efficient. So it's possible to send this piece of information with this many bits, but it may be possible to send the same piece of information with fewer bits. Computers and the internet are fast, but they're not infinitely fast, and so sending the same information with fewer bits, all else being equal, is more desirable than sending it with more bits. And a third thing that a code should do, and this is what maybe comes to your mind when you hear the word, many codes at least are designed to ensure confidentiality. So if you're doing credit card transactions on the internet, You want the merchant at the other end to be able to read your credit card number, but not somebody along the way who just happens to be electronically spying on you. Let's take these one at a time, and in particular this lesson is going to be mostly about accuracy with a little bit about efficiency, and then confidentiality will be taken up in a later lesson. Error detection and correction. The way this works is that you code information in so-called information bits. The notation we'll use is A sub 1, A sub 2, A sub 3, A sub 4, and so on, however many bits there are being used to transmit information. And then just like we had check bits or check digits in ISBN and UPC, now we'll have a check bit, or maybe more than one check bit, that's tacked on to the end of the message word. And we'll use C's for those, so C1, C2, C3, etc. And then the actual code word consists of the message bits followed by the check bits. In the example here, I have 4 message bits and 3 check bits, and that's going to be called a 7-4 code. It has 7 bits total, and 4 of those bits are being used to transmit message. Now, suppose I decide to come up with a code word scheme that looks like this. The 3 check bits are determined as follows. I take some combination of the message bits, add them together, and mod by 2. I have to do this mod by 2. When I add things together, I can get numbers larger than 1, but in a binary code, binary stream like this, I'm only allowed to use zeros and ones. And remember, when you mod by 2, you only end up with either a 0 or a 1. So let's do an example. If I want to send this message, what is the full code word? In other words, what check bits do I need to add on the end to make this a full code word? Okay, I need to figure out 3 check bits. There is a C1, a C2, and a C3. By the way, this is definition. It's not something you're supposed to know. It's just whoever's setting up this code says this is how it's going to work. So let's take their choice and work with it. C1 is computed as A1 plus A2 plus A3. So notice here is A1, A2, A3, here is A4. And so A1 plus A2 plus A3 is 0 plus 1 plus 0. It's 0 plus 1 plus 0. And then that is to be computed mod 2. So alright, that is 0 plus 1 plus 0 is obviously 1 mod 2. And what is that? Well, 1 is an odd number, so mod 2, it's 1. C2, similar thing, except I take the first, third, and fourth message bits and add them together. So first is 0, third is 0, and fourth is a 1. Mod 2. And that also turns out to be a 1. C3, take the second, third, and fourth message bits and add them together. So that's a 1 plus 0 plus 1 mod 2. And that is 2 mod 2, which is 0. So I've computed the 3 check bits, and the word then is, I take the 4 message bits, 0, 1, 0, 1, and tack on the 3 check bits in that order, 1, 1, 0. And here's the full 7-bit code word. You might want to stop the video and do this example. Alright, so C1, add the first 3 bits together, 0 plus 1 plus 1, mod 2 equals 0. C2, the first, third, and fourth. So 0 plus 1 plus 1. It's also a 0. And C3, 3, the second, third, and fourth is a 1 plus 1 plus 1 mod 2. That's 3 mod 2, which is 1. And so the word is 0111001. Okay, I've just worked a couple of examples here, taking the 4 message bits, coming up with the 3 check bits to add to make the full 7-bit code word. Now, to save time, let me just say, do them all, and here's what you get. So notice that we did, for example, the 0101. We did E, the letter E, and came up with 110 as the 3 check bits to add on. And we also did 0111, that's a G, and came up with the full code word for that. So I've done the rest of the letters space through H, and here are the full code words then. And now I'm a receiving computer and I receive this bit stream, and the question is, what message was sent? Okay, notice this time we're using 7-bit code words, so the right thing to do is to take 7 bits, 7-bit groupings like this. Okay, and then you take each 7-bit word and you go back to the alphabet and look it up. So here is an F. Here is an A. Here is O. That's not a word in my dictionary. It's not a valid code word. So let's skip that for the moment and go on, and here is an E. Alright, we're in a very realistic situation. The computer is receiving information over the internet, and 3 out of the 4 letters I can decode, and then one of them seems to have an error. So now I have to decide whether I'm going to do one of 2 things. Either send back a message to the other computer saying, there's a mistake, could you send this word again? Or I can say, what do I think this letter is? Now, you have to be careful here. It's not just a matter of taking a guess and going on with it. This may actually be banking information. Somebody may be sending numbers, numerical amounts of money, and if you make an error in that and take a guess, what you could have done is bankrupted someone if you guessed 3 instead of a 9 or something in a high position, a position that's in the thousands or tens of thousands column. You could have destroyed a lot of money. So it's not a good idea to guess unless you have really good justification for doing so. There are actually a couple of ways we could think about it. One is to compare what we see here with what valid English text is available. So F-A something E, and we might say, well, I don't think it's an A because F-A-A-E is not a word, but it might be C, F-A-C-E, or it might be D, F-A-D-E is also an English word. So in this case, just using the context of surrounding letters doesn't really provide the reason for choosing. Another thing we can do is look at the word we received, the words in the dictionary, and say, what am I close to? So 0001100, my choices, most sensible choices, would be a C or a D, and if you look at it, this word we receive seems to look more like a C, to be closer to a C than it does to a D. And so maybe the best guess would be that this is a C. a letter C, and that face was the word that was being sent. Let's try to capture that idea of being close. We measure closeness with some distance measurement. So like we can measure physical distance in miles or kilometers or something. In this coding theory, we can measure distance between strings as the so-called Hamming distance. It's the number of bits that are different. It's the number of positions in which the strings differ. One has a 0 and the other has a 1. So, to continue the example above, here are the valid 7-bit code words, and we receive this 0001100, and we're trying to figure out what that word might have been, most likely. Let's compute the distance, the Hamming distance of our received word from each of the valid code words. So I look at this and say, how many bits are different? How many positions are different between these two words? And well, it's this 1 and this 1 versus this 0 and this 0. So 2 bits different. The distance is 2. How about here? There's a 0 versus 1, a 1 versus 0, a 1 versus 1, 3. And if I do the rest of them, 4, 1, 3, 2, 5, 4, and 3 bits different. And then what seems reasonable to do and is the correct thing to do if you're going to try to do error correction and decide what letter or word was actually sent, you look for the position with the minimum distance. You look for the valid code word, which is minimal distance from the word that you actually received. So to help get a picture in your mind, the received word is here, and my possibilities were space, and I decided that's 2 units away, or A, and I decided that's 3 units away, or B, and I decided that's 4 units away, or C is 1 unit away, and I won't draw the rest. You keep going like this, and then you say which one's closest, and I've drawn this picture to illustrate that 1 is obviously the smallest distance, and so we just pick the word that's nearest. We pick the dictionary word or valid word that's nearest the word that we're actually have received and are trying to decode. Let me show you something related to this on Microsoft Word. You see this kind of thing when you use Word, if you use Word regularly. Let me type something like the normal thing to do, and you say, oh, I've made a misspelling. How do you know that? Well, Word comes ahead and flags with this red underline a misspelled word. That's not the only thing that Word may do. Sometimes it may do something like this. And watch carefully, the normal, N-O-R-N-A-L-E space, and whoops, that's not what I meant to do. Let me try that again. N-O-R-M-N-A-L. This is what I want to show. There is no such word as nor null. When I push space to indicate that word is done, Microsoft Word immediately corrects it to N-O-R-M-A-L. So different things have happened here. In the first case, there's been error detection. Microsoft Word has detected that this N-O-R-M-A-L-E is not an English word, so it underlines it, but it hesitates or refuses to try and guess what is happening. The reason may be that in its dictionary, this underlined string of characters is not close to any valid word, and so it doesn't have a logical choice to make. Whereas when we typed Nornal, it said that's really close to the word normal, and it's not as close to any other word I have in my dictionary, so I'm going to guess that the person meant to type normal. Again, example of error detection and error correction. And what happens depends on the mistake that is made and the dictionary that Microsoft Word is actually using. Of course, if you come up with new words that are not in Microsoft Word's dictionary, there are ways to add them to the dictionary so that they are no longer flagged as errors. Let's talk now about the error detection and correction capability of a code. Let's look at a really simple example, a so-called 3-2 code. So remember, the 3 means that there are 3 bits in a complete code word, and the 2 means that 2 of those are message bits, which means that the remaining bit is a check bit. And here's how this code is supposed to work. The check bit will be A1 plus A2 mod 2. So first, let's list all valid code words. Well, first of all, how many are there going to be? And to answer that question, I have to realize that there's a difference in jobs between the message bits and the check bit. The check bit does what it needs to do, and its assignment, I don't get to choose what the check bit is. There's a formula for determining that. But the message bits can be assigned as I want to carry information. The only thing I have to realize is that this is a binary code, so they can only be either a 0 or a 1. And so there are 2 choices for A1, either 0 or 1, and then there are 2 choices for A2, either 0 or 1. And those choices are independent, so remember that we multiply the number of possibilities. So 2 times choices times 2 choices is 4 choices total. Let's list them then. A1, A2, C1. In order, I could have for message bits 0, 0, or 0, 1, or 1, 0, or 1, 1. And those are the only 4 possibilities of 2 bits. Then to compute the check bit, I add them together mod 2. So 0 plus 0 is even, 0 plus 1 is odd, 1 plus 0 is odd, and 1 plus 1 is even. So here are the 4 code words. Now, to illustrate the idea of distance, I'm going to take this cube and put the code words at the vertices of the cube. There are 4 valid code words, but there are actually 8 2 times 2 times 2 strings of 3 bits. And there should be a 1, 1, 1 right here. So question, which of the code words then are possible code words are actually valid by our definition of the check bit? So we found that 0, 0, 0 is, and 0, 1, 1, and 1, 0, 1, and 1, 1, 0. Why am I doing this? Well, I'm trying to illustrate why the answers to the questions below are as they are. So how many incorrect digits or bits is the code able to detect? Think about it this way. A computer is sending a valid code word, one of these 4 it has to be, and then an error is made in one of the bits, and maybe an error is made in another bit, and maybe an error is made in another bit. How many times can we make an error like that and still have the computer at the other end say, ah, bad code word? Well, suppose the computer at the beginning is trying to send the word 110, and suppose I make a mistake in one of the bits. Well, I could make a mistake in the first bit, it's supposed to be a 1. Suppose it accidentally got flipped to a 0. Where on the cube would I be? Flipping to a 0 would put me at 0, 1, 0. That's back here. Is that a valid code word? No. So if an error was made in just the first bit, that error would be detected because the resulting word would not be a valid code word. How about if the second bit were flipped? Then I would go to 1, 0, 0. That's over here. Is that a valid code word? No. So an error in the second bit would also be detected. And in the third bit would change me to 111. That's up here. That's not a valid code word either. And so if I flip any of the 3 bits, I do not get a valid code word, and the receiving computer then would be able to detect that error. What if 2 bits were flipped? Say the 1 at the beginning got flipped, and then the 0 at the end got flipped. And so now I would end up here. Is that a valid code word? Yes, it is. And so the receiving computer would not be able to tell that an error was made, that this was what was actually transmitted, but that 2 bits along the way got flipped and I ended up here. So how many incorrect digits is the code able to detect? It's able to detect 1, and only 1. So to write something down about that, if any 1 bit of any valid code word is incorrect, the resulting word will not be a valid code word. How many incorrect digits or bits is the code able to correct? Remember, in the Microsoft Word example, sometimes the computer will go ahead and correct. Suppose I start with 110. The transmitting computer sends this information, and say the first bit gets flipped and takes me to 010. Now, I don't know that that happened. I'm the receiver. I'm at the end, and my computer receives this word, and it says, first of all, well, it's not a valid code word. Must have made a mistake. Which valid code word might have been sent? Well, this valid code word is distance 1 away, but this valid code word is also only distance 1 away. And if I don't know where the error was made, in which bit the error was made, I have no reason to prefer one of these choices above the other. And here's a situation where it would be a bad idea to guess. I just have to randomly guess between these 2 possibilities. And again, if this were financial information or something, making guesses like that with no more basis for judgments, not a good idea at all. And so the answer is 0. If just 1 bit of a valid code word is incorrect, there is a tie for distance to the nearest valid word, so we can't decode. And by the way, that's the right thing to do. If there's a single nearest neighbor, then you decode as that word. So back here, when we were trying to decide what this letter was, C, the letter C, was the single closest valid code word to the word that we received. And so we go ahead and correct the received word to what we think it is. But if we had a tie, if this 1 had also been a 2, and then there would have been a number of smallest distances, if there's a tie for the smallest distance, the right thing to do is not to decode at all. You can detect that error, but you shouldn't attempt to correct it. Okay, that's a lot of work actually to build a cube like this, and if we had longer code words, and we usually do, you can't do it geometrically anyway. So here's a nice theorem that will let you do that. If you're trying to decide how many bit errors a code can detect or correct, first compute what's called the weight of the code. This is the so-called weight of the code. The book's notation for that is T, and it is the minimum Hamming distance between any two valid code words. So if I have a set of code words, what's the distance between this and this, between this and this, between this and this, between this and this, and so on. Do all those comparisons and then take the smallest number that I get. It turns out there's a much easier way to do that. If you're looking at a code, what you can do is say, let's only consider the non-zero code words. So in other words, if there's something that consists of all zeros, like here, discard it for the moment. Don't think about it as you're proceeding to answer the question. And then say, what of the remaining words, what's the smallest number of ones that occur? Well, this word has 3 ones, 4 ones, 3, 3, and so on. And 3 ones is the smallest number of ones that any of these code words contain. There's actually a tie in a number of words for 3, but 3 is the smallest. So the theorem says once you've found that weight, then T, then the number of errors the code can detect is T minus 1, and the number of errors the code can correct is T minus 1. Work that out, then divide by 2, and then round down if the result is not an integer. So example, regarding this 7.4 code that we were using earlier, we pointed out that T equals 3. This code has weight 3. And so how about detect? How many bit errors can we detect? T minus 1 is 3 minus 1 is 2. And how about correct? T minus 1 divided by 2 is 3 minus 1 divided by 2 is 2 over 2 is 1. So on this 7.4 code, again, this was the example with the word face, we can detect 2-bit errors. If I must make a mistake in 2 positions of any valid word, I can still say, uh-oh, mistake made, and I can correct up to 1 error, and that's what happened here. We made presumably a mistake in 1 bit of the letter C, and we were still able to, from the receive code word, we were still able to recover the fact that that must have been a letter C. So detection is easier than correction, and so most codes can detect more errors than what they can correct. Alright, finally let's look briefly at efficiency. This business of using a code that sends information with the minimal number of bits. Before we go to binary codes and discuss this, let's look at another code that's been around a long time, Morse code, which is really a binary code. If you don't know anything about Morse code, it consists of a system of dots and dashes, and back in the late 1800s in particular, when telegraphs were being used to convey information, the operator would sit at one end and type out on an electrical signaling device sequences of dots and dashes. Then at the other end, a magnetic key would trip, and the operator at the other end would listen to the corresponding sequence of dots and dashes and be able to tell what was typed at the other end, which might have been miles and miles away. So suppose here is a stream of dots and dashes received. What was the message sent? Let's see, 2 dots is an I, and then there's a C, and then an E, and then B, E again, R, G. So for something from the late 1800s, early 1900s, being able to send the message iceberg to another ship might have been a very valuable piece of information. So ships surrounding the Titanic tried that very thing, but the communication wasn't received and heeded properly. How about this? What's the decoding for this stream of dots and dashes? And you say, oh, wait a minute, this is a lot harder because there are no spaces, and so how do I start out? Is this a dot, or a dot dot, or a dot dot dot? What is the breakdown of which sequences are to be lumped together? So almost impossible to decode by hand other than by brute force trial and error, and there would be a lot of possibilities to consider. So I happen to have made this example, and so I know that you're supposed to break there, and there, and there, and there, 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 and that's it. And so now it's easy. This is S, T, A, R, B, O, A, R, D. So if one ship is telling another that there's an iceberg ahead, it's also useful to give some information about which site it might be on and which direction you should turn. The point I wanted to make, though, is no spaces means that this is a hard problem. And so as computers construct codes, this is something to think about. How was this handled in Morse code? Well, the telegraph operator would literally pause between letters slightly, and the person listening at the other end could listen for those pauses and know when a code word stopped and the next one began. And I'll come back to that in just a moment. Before we do that, why were these particular combinations of dots and dashes chosen for the letters? This is what's called a variable length code. For example, the letter A has a code word that's 2 characters long, whereas the letter B has a code word that's 4 characters long, and the letter T has a code word that's only 1 character long. Why this particular combination? Well, if you look at what's on top of the screen right now and what's on the bottom of the screen right now, this is a frequency of usage chart for English. Take many pages of English text, an entire newspaper, say, and go through and tally what percentage of the letters used are A's, B's, C's, D's, E's, and so on. Then you look at this and say, well, obviously some letters are used a lot more often than others. So E, for example, is the most frequently used English letter, whereas things like Z's and Q's are used very infrequently by comparison. And so if you think about it, the goal of this unit is efficiency or data compression. And this was exactly done by the people who invented International Morse code, saying that, okay, I'm going to be typing a lot of E's. E's are used frequently, and therefore it would be a good idea to make the code word for E to be short, because I'm going to be using that a lot. How about we make it short so that when it does come along, I don't have to type very many strings of dots and dashes. Whereas I don't really care if the word for Z is pretty long. I don't have to use that letter very often, and so the longer words get assigned to the less frequently used letters, and the shorter words get assigned to the most frequently used letters. E and T are the most frequently used, so they get dot and dash respectively. Let me come back to how can the end of a letter be detected in a code? This business of why was starboard hard? There were no spaces, so what can I do about that? 3 possibilities. One is to use a fixed length code. Notice that's what we were doing in the previous discussion. This was a 7-4 code. Every code word was exactly 7 bits long, and so there was no question where the words should be broken apart. For example, it was no problem to get this question started. I just count out 7 bits, draw a line, 7 bits, draw a line, and those are where my code words are being taken from. There's a problem with that. It doesn't let me use the idea of Morse coding. Morse code says, no, for reasons of efficiency, make the commonly used letters have the shortest code words and less commonly used letters have longer code words. If I'm using a fixed length code, then I can't take advantage of efficiency. Can't make code efficient by giving shorter words to the most common characters. Well, how about I put a pause between letters, or maybe some other special symbol? That's what Morse code operators did. They physically paused, and the operator at the other end could hear those pauses. It turns out that doesn't work for computers. If you're sending information over the internet, the communication comes in spurts. So because at different times the same signal may be routed through different routers, routing computers on the internet, you can't say that if I'm emailing somebody in San Francisco that the speed at which I'm typing is exactly the speed at which the computer at the other end is receiving. So computers, because of the way the internet works, can't use pauses like this. Can't be used by computers. There is no timing information like that carried on the internet. And a third possibility is to use a code in which no code word is the leading part of a longer code word. Let's do an example of a code construction that illustrates that. Suppose I'm designing a code for a football coach to call in plays to the quarterback. So possible messages to send are run, pass, punt, call timeout, or another option that I personally think should be used more often is forfeit the game and let's all go home, because it's already been decided. I mean, when the score is 49-0 and it's the fourth quarter, what really is the point of finishing that game? Should forfeit and go home so we can do something better with our time. But that's just my personal opinion. Suppose that run plays are going to be called 45% of the time, pass plays 25% of the time, punts and call timeouts and forfeit and go home shouldn't be used very often. Let's design a variable length code word, and let's use principle number 3 here. So run is going to be used a lot, and so I would like to give a very short code word to it. Let's make this be a binary code, 0s and 1s, and so I'm just going to assign the code word 0 to a run play. So most frequently used word gets shortest code. Now, by principle number 3, the rest of the code words cannot start with a 0. It can't be like 0, 1, for example, because then if I received a 0, I wouldn't know whether I should say, oh, that's a run, or I should say, oh, I better wait for some more bits to come along to finish the word to know what to do. So all of the other words must then start with a 1. And when I receive a 1, then I know that it's not a run play and I should listen for more information. So how about then we let pass be 1, 0. If I receive a 0, I know it's run. If I receive a 1, I listen further. If I then receive a 0, I know it's pass. And that means the rest of the code words can't start with a 1, 0. So they have to start with a 1, 1. Okay, but I can't have 3 code words like this having the same code, and so we had better tack on something else. How about this be a 1, 1, 0? Then the rest of the words can't start with a 1, 1, 0. So I have to do this. And then the next most commonly used word is call timeout, so I'll add a 0 here like this. And then there's one word left, and I could continue the pattern and say it's 1, 1, 1, 1, 0. Or since I'm done now, I could just say, okay, I'm going to make that one a 1. And now this does implement number 3 above. When I receive the start of a code word, there's never ever any question about what I'm supposed to do. Either I know the word is done and I can decode it, or I know that it's not done and I'm supposed to keep waiting for some more of the word to come in. When you receive a message, how can you detect the end of a letter? You receive a 0 or the 4th consecutive 1 in this particular example. Those are the 2 ways that I can tell that a particular code word has been fully now received. So how about if this string of bits come in? What sequence of plays was called for? Well, 1, okay, I know I should keep listening. 1, I should keep listening. 1, 1, 0, I should keep listening. No, 1, 1, 0 is a valid word, and I know that's done, so punt has been called. Now I keep going. 0, oh, that in itself is a valid code word, so the next play called was run. Then 1, 0, there's a valid code word, so then a pass was called. And then 0, a run was called. Then another 0, a run was called. And then a 1, 1, 1, 0. All of that is a timeout. So notice there are no spaces here, and not all of the code words are the same length, and yet I was able to decode this without any question because of the way this particular code was designed. We'll not get into it, but you can glance through the section in the book on Huffman coding, and this is very similar, a simpler example, but very similar to how some computer codes that are used on the internet are actually constructed in order to achieve efficiency in information compression like this without having problems at knowing when letters do stop and start. And we will talk about security or confidentiality in the next lesson. Thanks.